Welcome back, fellow physicists, to Chapter 28 and Reflection and Refraction. These are the two general principles that govern the propagation or traveling of light. And we all probably have some idea of what reflection is. We can see the reflection of the computer screen here in the board, right? We've all looked in mirrors, we know what reflection is. Light essentially bounces off of surfaces. And if it didn't, you wouldn't be able to see yourself in the mirror. Or if we were in the classroom together, we wouldn't be able to see each other, and so on. But why and how does light reflect? Well, let's start with why, shall we? We already know that light can interact with the electrons in atoms, like in hydrogen gas lamps, helium lamps, neon lamps, etc. Light is also known to have a certain amount of momentum, thanks to the brilliance of Max Planck and Albert Einstein. That, incidentally, is why we say that light exhibits the particle-like qualities, right? Because only particles, things that have mass, can have momentum. Remember, momentum is mass times velocity. In any case, light is known to have a certain amount of momentum, so that when light hits the electrons on the surface of a mirror, they hit it like a bumper car, they bounce off. But the atoms also have mass, so the electrons initially bounce back. It's actually much more complex than that. The atoms actually absorb and re-emit the light, and the momentum of the light tells the atom where to reflect it. So how does light reflect? Well, we usually say that it obeys this thing we call the law of reflection. So let's say you've got a plane mirror, P-L-A-N-E, like flat, like what you have in your bathroom. Okay, this is the surface of the mirror here, and let's say that some light comes in here. Where is it going to reflect? Well, if the light is traveling in this way, it's going to reflect out that way, right? Now, there is a mathematical relationship that governs this. If this dashed line here is the normal, or the line that is perpendicular to the surface of the mirror, we're going to call this the angle of incidence, and we'll call this the angle of reflection. And the law of reflection states that the angle of incidence is equal to the angle of reflection, both measured from this normal, or from this line that is perpendicular to the surface of the mirror. In any case, that's what we mean by this. By convention, we take these angles with respect to the normal. You'll notice that there's nothing in here about frequency or wavelength or whatever, because those things don't change. And that also means that the wave speed, or the speed of light, does not change just because it gets reflected. That's great. Okay, what does that mean? Well, I would have really liked to have shown you a demo of lasers reflecting off of things going in straight lines and so on, and how a mirror actually works. But because I'm unable to do that, I have included a link on the Chapter 28 lecture page that goes to Dr. Alejandro Garcia's video on mirrors. It's actually pretty helpful. Also, you can find stuff about lasers traveling in a straight line in his lecture series. In any case, suffice to say that if this was a laser beam, it would appear to go straight, right? And it would appear to go somewhere out here, but it's really going this way, but it looks like it's going in a straight line. If your eye was here and you were looking, you would see where the laser appears to go, right? Okay, great. So how is it that we can see an image in a mirror? Well, let's start with the simple case, the plane mirror, right? When you looked at yourself this morning, you saw an image of yourself. The light from various parts of you reflected off the mirror and back to your eye, and in so doing, it appears that there is an image somewhere out here, right? If you're standing here, it looks like there's an image of you on the other side. that image is called a virtual image because the image of you doesn't actually exist inside the mirror, right? The mirror is only about this thick, and all of this virtual space behind the mirror doesn't actually exist. So, how is it then that you can see yourself in a mirror? Well, so let's say you're here, right? So light from your foot is going to go and bounce off to your eye, right? And so it's going to look like your foot is over here inside the mirror. Light from the top of your head is going to bounce off here and back to your eye, and so it's going to look like the top of your head is up there. Light from your hands is going to bounce here and then up to your eye, and so it's going to look like, if we follow this straight line from the eye, it's going to look like your hand is there inside the mirror, right? So light actually goes this way to your eye, following the law of reflection. The same thing is going to be true here if you want to bisect both of these angles. And that's how you end up with this virtual image inside this mirror space that doesn't actually exist. That's different from a real image. A real image is some place where light actually comes from. Like if you look through your glasses and you see something, you're seeing where the light actually is coming from, right? If you can see through the glasses and look at the board, the light is actually coming from the board, right? That's different from a virtual image like inside a mirror. Not all mirrors are flat, however. Some mirrors are curved inward. We call those concave. And some mirrors are curved outward. We call those convex. And those, I would have really liked to have shown you myself, but because I haven't, I've also included links to a series of demonstrations for concave and convex mirrors on the Chapter 28 lecture page. So this is maybe a good time for you to take a brief pause and go and have a look at those. Now, if a mirror is scuffed up, so it's not a nice, shiny, flat, reflective surface where the light is reflecting off of a rough surface, then we don't see an image. Why is that? Well, because the surface is not a flat plane, right? And it can't reflect all parts of a coherent image, like what you saw in the mirror this morning. And that about sums up the basics of reflection. But what about this other thing, this thing we called refraction? Well, I want to pose a question to you. This is called Fermat's principle, F-E-R-M-A-T. Now let's say that here's a beach, right? And out here's some water. And out here is the sand, right? This is the beach. So let's say you're here and you see, and you're working out on this beach as a lifeguard, okay? And you see somebody drowning in the water here at the O. Now, what is the fastest way to get there? The answer may actually surprise you. Generally, the most common answers are go in a straight line, which, you know, the shortest distance between 2 points is that one. Okay, there is maybe some logical merit to that, but unfortunately, human beings move about 10 times as fast on land as they do in the water, right? We're much faster on land. And so a lot of people think that if you go here and take the shortest path in the water, that's the shortest path. And believe it or not, neither one of these is correct. There's actually a path intermediary somewhere where you take most of the path, or most of the distance on land, and there's a slightly more time-efficient path here through a slightly longer portion of water. Now, unfortunately, the mathematics involved in finding this path are pretty complicated. It involves a branch of calculus called the calculus of variations. It's how we find things like the great circle route, or the route that the airplane that you're in takes across the surface of the Earth to get from one point to the other in the shortest amount of time. They call that the geodesic. In any case, let's say that now instead of this can actually still be water for the sake of argument. So this is water, and we'll say that this is air, maybe. Like if you were looking upside down at a glass of water or something. So if you were to, say, take a pen or a pencil or something like that, and you wanted to stick it in your glass of water, and I'm not going to do that because I actually intend on drinking this glass of water, but you can already very easily see that it looks like the pen is not moving in a straight line such as it is above the water, right? It looks like the line is bent. Now, there's a very good reason for that, of course, and that is that the water is more optically dense, right? There's a lot more particles of water in this volume than there are particles of air, say, up here or up here. And so the light bends as it goes through the water. Light actually moves more slowly in water because this is a more optically dense medium. There are more particles per unit volume. And so the light actually slows down as it goes into the water, causing it to take this sort of intermediary kind of path. Now, when light refracts into a more optically dense medium, it automatically takes the shortest time path possible to get from one point to another. And so it finds this sort of geodesic by itself. Anytime where you have some kind of medium like this, where it's more optically dense, that it's that such that light actually moves slower than it does in the vacuum of space, then we say it's a refractive medium. Refractive media are characterized by this thing we call a refractive index, or an index of refraction, usually denoted by a lowercase n. This lowercase n is the speed of light in a vacuum divided by the speed of light in the medium. That is, if you had some kind of refractive index, some kind of hard glass or plastic, that when light moved through it, it moved at half of the speed of light, you would have a refractive index of 2, right? Because 1 divided by a half is 2. That's how that math works. And that's why if you drop a coin into a cup of water, it looks like it's at a certain depth if you view it from the side, but it looks like a different depth if you view it from on top, right? Because the light actually moves slower in this different refractive medium. I know it sounds crazy, but light actually bends this way. And this explains all kinds of phenomena like mirages and such, like the heat waves that we can't see directly, but because they change the density of the air when the hot air current rises, it makes this funny waving pattern, causing that heat wave effect. Now, there is a law that relates how light bends going from one refractive medium to another. But that's not going to be required material for this course. I'm going to explain it to you anyway, just for fun. This is called Snell's law, and we usually say n1 sine theta 1 is equal to n2 sine theta 2, where the thetas, this would be like theta 2, and this would be like theta 1. The angle of incidence for the light in air and the angle of refraction for the light in water are going to have two different angles. And the ratio of the sines of those angles goes as the inverse of the ratio of their indices of refraction. Now what that really means is, if you have a medium where you have a very low index of refraction like air doesn't have a lot of particles in it in order to slow the light down, whereas water has a lot, right? So the angle of incidence here is going to be greater than the angle of refraction inside the water. That's what Snell's law means. This can very easily be explained by this funny thing we call Huygens principle, and that is the idea that if you have like a front of waves, like a bunch of light that's moving out together in a plane, something like that, then each point on that wave front can act as a source for its own waves. I know that sounds really funny, but if you look at the video, or the link to the video that I posted for Huygens principle, you'll see very readily what it is I mean exactly, and why it is that the light coming in from the air gets refracted toward the normal as it goes into a higher index of refraction like the water. Now, like I said, that if light goes from an index of refraction like the air into a higher one like glass or plastic, then the refracted angle is smaller than the incident angle. If the angle is something like 90 degrees or more, right, if you're going from water to air, for example, and this angle is 90 degrees or more, then the light will just get reflected inside the water instead. We call that total internal reflection, and that's how fiber optic cables work. Essentially, you have like some really high refractive index plastic, right? You have air on the outside, you have the fiber optic here in the middle. And the index of refraction is so high that even if you have like a really shallow angle or whatever, it'll reflect internally, right? This one will reflect probably more like this. But as long as it keeps reflecting the light internally, none of it gets lost and escapes the cable. And that's why if you put light in one end of a fiber optic cable, it always comes out the other side, no matter how it bends or whatever. That's also the reason that diamonds are so sparkly. Diamonds have a really, really high index of refraction. They have the highest index of refraction of just about anything that we know. And so the total critical angle, this angle here for total internal reflection, is actually pretty small, something like 24.4 degrees. And that's why diamonds have this funny kind of cut, right? Like this, because these angles are really small. And so if the light hits here, hits there, whatever, it'll just keep bouncing around and bouncing around and bouncing around on the inside. Now, that's not to say that light can't get out of diamonds. Obviously it will. Diamonds are generally pretty small, and so they're going to move very fast. The light moves at still a really fast rate. You're talking about, 3 times 10 to the 8th meters per second in a vacuum. Even if you're going at a fifth of that, you're still talking about moving really fast across a really tiny distance. And so the light is going to get out, but only at certain places, right, where the geometry of the light coming in and going out is favorable to that. And that's why, if you look at a diamond, not all of the facets on the diamond are shiny, but the ones that are sparkle real bright. Now, I wasn't able to show you the dispersion of light, of white light, myself, unfortunately, but I have included a link to a dispersion video. We all know what dispersion is. That's where you take incoming light, inclusive of all wavelengths, and you split it basically into a rainbow, right? As the light comes out, it splits into its component colors, red, orange, yellow, blah, 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 right? Why is it doing that? Well, obviously it's doing that because the light is actually bending, right? So if you have light going into a prism, obviously this is what's on Pink Floyd's Dark Side of the Moon, right? So if you have light of all wavelengths, it's going to split, because some wavelengths of light are going to bend more than others will. That gives rise to this dispersion phenomenon, this thing where we see all the different colors of light. Now, like I said, I don't have the equipment here, unfortunately, to be able to demo dispersion for you, but I did put a link to it on the Chapter 28 lecture page. Dispersion and total internal reflection are sufficient to explain this phenomenon that we know of as the rainbow, this thing we see in the sky when it's raining on one end of the sky and there's sunlight on the other end of the sky. So what happens is you'll have like a water droplet, right, as it's falling. So, and they're actually more spherical. They're not like this, right? That's the shape of something maybe as it rolls down your cheek or something, but not so much otherwise. So the angle for total internal reflection in a water drop is something like 48.75 degrees. And so it's sort of favorable for light to come in and bounce around and bounce around. And if you're this one particular color or wavelength of light, you're going to bounce off in a certain direction. So as the raindrop falls, so let's say here, it'll give you red, and then down here a little bit further, it'll bounce and then it'll give you orange, because that's the geometry that's going to favor getting to your eye. Down here a little ways, it'll be yellow or whatever, right? So there's a region of space where a particular wavelength can bend to reach you, and that's actually like a circular arc, right? So this whole thing would be like red, this whole thing would be orange, this whole thing would be yellow, and so on, and you get a separation of color bands. And that's what we call a rainbow. Ta-da! In any case, we need total internal reflection in order to explain the phenomenon known as the rainbow. Okay, do we know how pinholes make images? It's actually pretty simple if you think about it. So let's say you've got a little sheet of paper and you poke a tiny little hole in it, right? But the light source is like this, right? It's the sun almost going through an eclipse. Okay, so here we got bright light. I'm going to draw a circle here. Here we've got darkness. And so what we're going to end up with is brightness here and darkness on this side, right? That's not a very well drawn figure, I apologize, but this is why I chose a life of science instead of life of artistic expression, because I'm a terrible artist. But in any case, that's why if you make a pinhole, and they used to use this to make pinhole cameras, but a pinhole will show you exactly the layout of the light source itself. And if you look at the image that I posted, the first one, there were 3 on the chapter 20 lecture page. And the first one, you can see that the gaps in between the leaves and whatever make all these tiny little pinholes, all of which are shaped like tiny little crescents, because this image was taken just before the total solar eclipse that went over North America just a couple of years ago. Went up to Oregon to see it with some friends of mine, so I got a nice direct image of the eclipse, but also what was happening just beforehand, which makes that nice image. Now there's also another kind of object that focuses light the way that this pinhole thing does, and that is this thing called a lens. Now lenses basically come in 2 types. There's this thing called a converging lens, sometimes called a convex lens, right? And this causes light to come in and like focus to a single point, right? If you have a bunch of parallel light from like a light source that's really far away, it'll make it all converge. That's why it's sometimes called a converging lens, this convex lens. The other type is called a diverging lens, also called a concave lens. And if you have light from a distant source, then it'll spread it out. Now essentially what lenses do is focus light, but the way that they do it obviously is a little bit different, and this is how Galileo was able to make his telescope, which was not the first one to be made. A guy named Hans Lippershey, I think, made the first telescope, but Galileo was the first one to turn it toward the heavens and try to use it for astronomy. So let's say you've got an object that's really, really far away, like one of the Galilean moons or something, right? It's so far away that basically all the light coming from it is going to be parallel to it itself. And so that means all this light is eventually going to want to focus down into one spot. Now if you put a diverging lens here so that it doesn't quite focus down to a single point and instead diverges the beam again, what you have here is outgoing parallel light. And so if you put your eye up to that, you can see whatever was at this light source. Most modern telescopes don't quite do it this way. Also in most cameras and stuff, you have like you'll have a lens and then you'll have like an eyepiece lens, and both of them are converging, and so the light will go down to a single point and invert, and that's why lots of pictures and stuff appear upside down if you look at the actual film or something like that, or reversed depending on the geometry of the situation. Now I really wanted to try to take the optical bench and build you a telescope, but unfortunately that's not going to be easy to do. So you can look up telescopes and such if you like, and at some point in the future, if you want to come back and visit, I will gladly, especially if you take my astronomy class, I'll do my best to try to take you up to the observatory so you can see some of them firsthand. Now there are limitations to using lenses in telescopes, and one of them of course is the size of the lens itself. If you're going to have the correct curvature and you want to have a really, really big lens so you can collect more light, more photons, right? So you can see an object that's dimmer, fainter, farther away, however you want to say it, then this lens, the larger it gets, obviously the heavier it's going to be. Now if you have a lens that's maybe about 2 meters across, it's going to sag under its own weight and cause problems. So there is a hard limit on the size you can have for a lens. There's also this funny thing called chromatic aberration, and that really comes from this phenomenon that we know as dispersion, where you have a bunch of light that goes into a piece of glass and the colors split. The second two images, the second and third image, show chromatic aberration. First, the lines of the different wavelengths or colors of light splitting, and what that actually looks like. And if you look at the image of the little metal horse, you'll see that there actually appear to be more than one image. There's like a green image, or like a blue image, and then there's like a red image, right? And they're not in the same place. Now, if we took all of this parallel light and we focused it down and it hit some point, then we could say that that was the focal point of the lens, right? Parallel light always focuses at the focal point of the lens. If you know the focal distance of a lens, you can tell what the relationship of the distance from the object that whose light source or image or whatever is going to go through the lens, where it's going to make its image. So this is our optical axis. This is just the direction that light is going to travel. Here we've got a lens. Let's say this has a focal distance of 10 centimeters. So here at 10 centimeters, that's about the same, right? Here at 10 centimeters, if you had light coming in from some parallel source, the light would focus to this point. And if you put a screen there, you would be able to see the image of this faraway object, because all the light would focus there as a result of the curvature of the lens. But let's say that you've got some object that's not a million miles away or whatever, it's much closer, right? So let's say that you have an object here at 20 centimeters from the lens. Where is it going to make an image? Well, there's a relationship that governs how far an image is going to be in relation to the focal distance and the distance of the object from the lens. This is, by the way, supposed to be a converging lens. Now, let's say that the object is here, right? So I'm going to put a little arrow here to denote where it is. The relationship that governs where the image is going to be is 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. Now, the focal length is 10 centimeters. How far away does the image have to be if the object is 20 centimeters away? Well, we got 1 over 20 plus 1 over s prime is equal to 1 over 10. What does this have to be? Well, what if I said s prime is 20 centimeters? Is that right? Well, we got 1 over 20 plus 1 over 20. Is that equal to 1 over 10? 1 over 20 plus 1 over 20, that's the same as 2 over 20, or 1 over 10. And so, yes, the correct distance for this image should be at 20 centimeters. You can always solve the math this way. Usually it's not so difficult. I believe you should have a few practice problems in this vein for this chapter. But let me show you how to do this graphically. So if you take the first, what we call principal ray, going parallel along the optical axis from the object, right? Once it hits the lens, it'll go through the focal point and then continue on undeviated. This one will go straight through the middle, undeviated. This one will go through the focal point and then hit the lens and come out parallel to the optical axis. And these three should all meet right here where the object is, or the image, excuse me, of this object is going to be. Now you'll notice something here. At this distance, the image is not on top, it's on the bottom, and so that means whatever you see is going to be inverted. in any case, go ahead and try some of these problems yourself. Of course, email me if you have any questions, and I hope you've enjoyed this video on Chapter 28. See you again soon.